Getting into chapter 4, we'll be talking about the endocrine responses to resistance exercise. Remember, we're talking about the endocrine system. We're talking about hormones. Okay, and so with hormones, they get released because their primary purpose, a lot of ways, is to maintain a steady level of glucose going to the cells. And they're getting released because there's been an imbalance during exercise, primarily, burning up through our glycogen, and burn up through the blood glucose. So hormones are getting released to allow for a steady flow of glucose throughout to provide the energy for the system. Okay, and they also help out with repair, growth, things of that sort following exercise. But just remember that the endocrine response and hormones are doing so to help out maintain substrate availability, and that becomes important during times of strenuous exercise. Okay, so we'll be talking about testosterone, cortisol, catecholamines, growth hormone, insulin-like growth factor, and those are the primary ones we'll be getting into. There's tons of them. There's a lot, but for our purposes, there's just that select few that we're really going to be interested in talking about right now. To begin, keep in mind that when we're discussing hormones, we're talking about really endocrine response overall, because hormones get released from what's called endocrine glands. And so just keep that in mind, that when you hear the endocrine system, what you're discussing is hormones being released. Okay, and it says endocrine glands, body structures are specialized for releasing hormones into the blood. And hormones defined as a chemical messenger that are synthesized, stored, and released in the blood by endocrine glands and certain other cells. And so when you see the word messenger, and that's really kind of what hormones are doing, is when they hit a targeted cell, they start then a chain of reactions to then come about what the desired result is needing to happen. Such as when you run out of glycogen, you're running out of blood glucose, a lot of hormones get released to then stimulate different cells to start the production of glycogen or glucose, or turning another chemical into that. So that's really what hormones are doing. They're just messaging. They're targeting cells, and then they're turning cells on to say, start up this process of getting whatever it is, such as, whatever it is, be like glucose, to then be able to get out into the system. It says the principal endocrine glands of the body, along with other glands that secrete hormones. You can see them all right here. Okay, hypothalamus, pituitary gland, thyroid gland, the parathyroids, the heart, adrenal glands, liver, the pancreas, kidneys, and then in females, ovaries, and males, be testes. So those are the primary glands that secrete hormones, and the main target, like we just said, as a messenger in the last slide, the main target is going to be, for the most part, muscles. And these chemicals are, what they're doing is they're signaling out then another, when I say that by main target, the muscles is primarily the place where the hormones are going to be interacting with or wanting to send whatever they're signaling that molecule to. Because reason why is muscles, that's where metabolism for the most part is taking place. Okay, and so the signaling place, muscles are that part, because we are needing to get a lot of times fuel then to the muscles. Okay, if something's acting on the liver to stimulate gluconeogenesis or glycogenolysis or something along those lines like that, then what's happening is then you're hitting that to start production of glucose, then gets sent out to then generally the muscles then for fuel usage. These hormones are intimately involved with protein synthesis and degradation mechanisms that are part of muscle adaptation's resistance to exercise. Okay, and meaning by all that too is a lot of hormones getting released to then help out, ideally with, especially during resistance exercise, stimulating protein synthesis. Okay, testosterone, growth hormone are two of the ones will be of interest. They help out with muscle or increase in muscle as protein synthesis. Fortunately, there are some that do involve a protein degradation. Cortisol is a good example of one. cortisol gets released. It's a stress hormone. So that gets released, and a lot of times it does proteolysis. But it's doing so to help maintain adequate substrate for like adequate glucose or glycogen usage, then be able to use for the muscles. Now keep this in mind that all these reactions hormones can either be anabolic or they can be catabolic. Okay, if they're anabolic, they promote tissue building. If they're catabolic, they degrade cell proteins. Some hormones might be both. Some might just be one or the other. Insulin is anabolic, so it stimulates protein synthesis, also stimulates lipid synthesis as well. And of course, so it does work with glucose and glycogen. Glucagon is an example of both. It could be anabolic or catabolic. Okay, so just keep in mind that reactions are going to be one or the other or both. Because what we're doing is we're either breaking down or building up in order to maintain a proper supply of substrate usage then to be used for the muscles. So I've kind of maybe brought this up a little bit, but hormones, the way they work is kind of like a lock and key type of situation. So you have a receptor, you have a special hormone that fits perfectly like a lock into a key onto the receptor. And at that point, when that happens, then you start the chain reaction of then, like it says, acts as a messenger, starts a chain reaction then to start the reactions to get whatever it is that hormone specifically targets. It says the inability of a hormone to interact with a receptor is called downregulation. A lot of hormones, what happens is when they're not needed, you'll start to change the conformation of these proteins, because really these receptors or hormones, they're protein based. So you'll change the shape of them, which will in turn not allow the lock and key to fit properly. So therefore you won't have then the chain reaction taking place at that point. So that's referred to as downregulation. Categories of hormones, two primary ones is steroid and non-steroid. So your steroid hormones, it says they're fat soluble and passively diffuse across the cell membrane. So the example they're showing here is testes produce testosterone. Testosterone, it's main key ingredient for making your sex hormones, testosterone, estrogen, is cholesterol, which is a lipid. And so what happens is that if you're a steroid hormone, they could just pass right through the cell membrane and then start working on the targeted cell, whatever it is that it's going to, whatever's supposed to help out with. Okay, a lot of times they look at gene formation, so DNA, RNA, and all the processes with that, looking at different hormones that help to target that type of rearranging. Okay, testosterone, that's why supplemental testosterone, that is anabolic steroids, has that effect, is because it's able to cross the cell membrane, but then once it gets into the cell, it then starts immediately working. You can see like this one right here working on the DNA. And we know, assuming that you're training, lifting properly, eating well, anabolic steroids, the net result is going to be an increase in muscle mass. So that's how steroid hormones work. And then you got non-steroid hormones. And it says here polypeptide hormone interaction. So they're like sometimes referred to as non-steroid. And so these need a second messenger or a carrier to get into the cell. Okay, and so what happens is as once they reach the cell membrane, they hit with a carrier, then that brings it in, a second messenger, then at that point, then it will start going through the processes that needs to work on as well. Okay, and you can see right here, this working on gene. Both hormones are all working on DNA, RNA, because they're speeding up, slowing down, and so they'll work on them, but non-steroid need a carrier to get into the cell. So they just can't passively diffuse across the cell membrane. And then here you see growth hormone and insulin are examples of a polypeptide. So when you see, I don't know if I said this, but polypeptides are just protein based. And so but they do need a second messenger or a carrier to get into the cell. So looking at amine hormone interactions, so examples of synthesized from amino acid, so tyrosine, tryptophan. The tyrosine is going to be epinephrine, dopamine, tryptophan being serotonin. It says bind the membranes via second messenger, and then these are not regulated by negative feedback. So what negative feedback is it's a sensory process that when these hormones are being produced and released, when it gets to the too high amount, then it'll send a feedback back to the brain, to the CNS, to say stop producing this hormone. And that's what negative feedback said, and it'll operate this way. So you got heavy resistance to exercise and hormonal increases. Hormones are secreted before, during, and after the resistance exercise bout due to the physiological stress of resistance exercise. And they found as few as 1 or 2 heavy resistance sessions can increase the number of androgen receptors in the muscle. It doesn't take a whole lot to start having a response to training, especially when you're looking at the endocrine response. Now, granted, the harder you train, the longer you train, you're going to have a greater response. And then ideally, over time, that greater response will lead to greater adaptations. And so that's something just to know as you're training. It doesn't take a whole lot to start getting a response, but the greater the response will be due in part to the harder you train. And you can see the specific point, key point meaning the specific force produced in activated fibers, stimulates receptor and membrane sensitivities to anabolic factors, including hormones which lead to muscle growth and strength changes. Okay, and that's kind of the goal of why we train, because we're trying to put ourselves in a negative spot, I guess. And then hormones are getting released to try and get everything back to equal. And so this is just the SAID principle, which we'll talk about coming on here in the later chapters, but SAID principle is specific adaptations to impose demands. That is, you're going to get a specific adaptation to specifically how you train, more or less. Okay, so if you want to start getting muscle growth, strength changes, then you need to train with a high force to really put the muscles in a negative spot. And then at that point, then hormones will get released to try and help rebuild, get back to a greater level than where you once were. And so it's just this constant back and forth, back and forth, back and forth over time, which will then lead to then ideally muscle growth and strength changes. It says a combination of many different mechanisms is thought to stimulate exercise-induced hypertrophy. Okay, and it is. There's this stuff in that we're still learning right now. We're studying a lot. We really don't know exactly all the ins and outs of hypertrophic changes. So there's a lot of that we don't know, but we do know to some extent that through training, these hormones acting on the nucleus, on the genes, there's some kind of interaction going on there that, like I say, the molecular signaling, something going on, working on those genes that's causing then an upregulation of specific genetic factors leading to hopefully the muscle gain, muscle strength increases. We're just not sure exactly how all that is taking place, but we do know that hormones are acting, they're helping out increase molecular signaling. And so for some of them, like testosterone, growth hormone, we're trying to up as much available of those hormones as possible, because the thought is that more is better in this situation. So if you have a lot more, because when testosterone, we'll get to here in a bit, you release testosterone and a lot of it gets bound up and used up really fast, because really testosterone just doesn't work on just muscle. Okay, testosterone does work on a significant other things in the body. And so once you have testosterone being released, some of it gets taken up already. They're kind of looking at the free testosterone, so leftover testosterone, I guess you could say. The more of that is shown that it does lead to greater strength and muscle increases. So that's why if you supplement with it, that is, you take anabolic steroids, that's kind of the goal, to try and get as much as possible. And if you do that with heavy training, because a lot of times guys will train with testosterone or train mildly, but then they'll take steroids, they don't get the muscle mass. They actually will gain fat because, like I said, testosterone is an anabolic hormone. Anabolic is building up. Any time in the body you're building something up, you're in a state of anabolism. So putting on fat, technically you're anabolic. And so you got to be careful with steroids, is because you better be training and eating properly. If not, it could turn into fat. But assuming that you train properly, eating well, having extra testosterone will then help out, speed up, some of those processes you want. That is like muscle mass, strength increases, things of that sort. It says hormone responses are tightly linked to the characteristics of the resistance exercise protocol. So, point being, there's going to be a different response based upon if you're running or resistance training, or if you're doing endurance type resistance training versus strength resistance exercise. So doing sets of 12 to 15 versus sets of 1 to 5. Okay, you're going to have a different response based upon what kind of resistance exercise protocol you're doing. It says peripheral concentrations in the blood. It says peripheral concentrations of hormones in the blood do not indicate the status of the various receptor populations or the effect of a hormone within a cell. It says it's typically assume, however, that large increases in hormone concentrations indicate higher probabilities for interactions with receptors. That's kind of what I was saying already, that if there's a large amount of hormones, then you could kind of assume that there's going to be a greater interactions with cells. But sometimes what's in the blood doesn't always indicate exactly all the hormone says, because once hormones get released, they're being used up. And a lot of times, you test for like lactate, you test for ammonia in the blood, and these other byproducts. Sometimes what you're getting is not indicative of what actually was produced. Okay, so you got to be kind of careful. You can't just sit there and draw blood and say, there's this much in the blood, so that's it. No, there's a bigger picture to it all going on. So like for hormones, what you're seeing in blood might be a lower concentration than what was originally produced. But like I said, it's assumed, which means we don't really exactly know, but it's a safe assumption to guess, well, if there's a greater amount, if we have X amount in the blood, but then we do something and we have a greater amount in the blood, we can assume that greater amount of blood will then help out with a greater reaction with the cells. It says physiological mechanisms that contribute to changes in peripheral blood concentration of hormones with exercise. So your circadian rhythm, blood fluid volume shifts, tissue clearance, venous blood, pooling of blood, hormone interactions with binding proteins. So those are all different mechanisms that can have an impact upon concentrations within the blood. So the adaptations that are possible with training, especially the endocrine system, because all systems within the body with exercise will get more efficient. It's just like sweating, where sweating is a response of hormones being released, but your endocrine sweat glands, with training, they become more efficient. And so they allow for better regulation of body temperature without having a huge shift in blood flow to help out to sweating. So your endocrine glands for sweating, for instance, will start to release water. They'll start to sweat a lot faster at the onset of exercise. So actually a training adaptation through endurance training is if you start to sweat sooner, that's a training. Your body's starting to adapt and cool itself off. And those endocrine glands are able to sweat a lot faster because, well, they're able to do so without having a huge redirection of blood. Because we carry the heat in the blood for the most part. And so we're not going to have a huge change in blood flow to the skin right away for those who are trained. And so because those glands are they're going through adaptations. So that's just a really strong example of how glands, just like our endocrine glands, everything gets trained and gets more efficient essentially with exercise. So some adaptations, you get the synthesis and storage of hormones, greater amount to be able to be stored up and also to be used, and then also be able to make them a lot quicker. It says time needed for clearance of hormones through liver and other tissues. This gets into when we're talking about bioenergetics, talking about EPOC. One thing we see in the exercise response, or in the body response to following exercise during the EPOC, is a high body temperature. Well, and that's, it's when you're done exercising, you're sweating for a really long time. So the more trained you become, that EPOC essentially gets more efficient, gets shortened up. You're able to regulate temperature and sweating, which those are both responses to a release of catecholamines. And so as you train, as the glands get better, well, you're able to clear out hormones, maintain regulation of the body a lot better, especially then. This is during exercise, but also then following exercise as well. You can influence the amount of receptors in the tissue, changes in the contents of the secretory cells in the gland, secretory cells in the gland, and the degree of interaction with the cell nucleus. So more or less what's going on is you're getting a better overall regulation of our endocrine system, of our hormones being released. The body just fine-tunes it so much to where you're only producing, releasing what you need, maintaining it. It's just a lot more efficient overall. Main anabolic hormone, testosterone, is probably the most common one. Gets released from the testes. That's where it's produced. Okay, and its influence is, well, we all know it increases muscle mass, helps with strength. When I say muscle mass, I should say protein synthesis. And so that's what the most common ones we're associating with is that. It's going to change up based upon, obviously, how you lift. And it's going to be different between males and females. Okay, males will have, you see the very bottom, females have about 15 to 20-fold lower concentrations of circulating testosterone than men do. Okay, that's the reason why men are bigger than females, because we have a higher amount of testosterone normally, or just naturally. So therefore, there's why we have a greater muscle mass. Our body structure is bigger. So this is one reason why we're stronger and bigger than females, is just due to the higher amounts of testosterone within males. I've also found too, if you want to get a little bit more testosterone circulating, we'll train hard and train heavy. You see right here, greater concentrations following deadlift or squats. So you're looking at large muscle groups, big compound, multi-joint, multi-muscle group exercises. Training heavy, 85 to 95% of your 1RM. Moderate to high volume of exercise. Volume is looking at reps times sets. You also short rest intervals. And then 2 years or more of resistance training experience. So the longer you train, the more the body will start to release. Going back to the last slide. It says free testosterone sex hormone binding globulin. So that sex hormone binding globulin, that's kind of what I was talking about. When testosterone gets released, it gets used up, it gets bound up. So they look at a lot of times that along with the actual just free testosterone floating around. It says free testosterone counts for only about 0.5 to 2% of total testosterone. Thus, higher total testosterone concentration allows for more free testosterone. That's why, once again, taking anabolic steroids, one thing, trying to get as much of that free testosterone floating around to be used specifically, ideally for, especially in conjunction with heavy training, like you see in the next point. If you're doing heavy training, that free testosterone then will ideally be used for muscle growth and strength. As I said, a heavy resistance exercise, 6 sets of 10 repetitions at 80% of 1RM. So that's why you see most guys who are taking testosterone, they're lifting super heavy, super long. And that's a good thing about testosterone, is it does help out immensely with the recovery. And that's kind of a lot of ways how it actually does work, is it allows you to keep training at the same intensity day in, day out. Okay, you look at East European countries, those who, for Olympic weightlifting, have done steroids for the whole history. But if you go back to, I know I talk about this in Next Phys, but you talk about the country of Bulgaria. Bulgaria, to my knowledge, I forget how big it is exactly, but it's smaller than the state of Texas. It's like half the size of the state of Texas. Well, if you look at their Olympic weightlifters for a small country, we're pound per pound the strongest, best weightlifters throughout the 70s, 80s. They're always competing against the Russians, and we all know how big Russia is. And so if you look at the Bulgarians, they had a coach named the Mad Butcher. There's a reason why his nickname was Mad Butcher. Not that he killed anybody, but that he just was able to take at these lifters and just make them into just phenomenal freaks. What people don't know, well, in the weightlifting community they know, but outside that is that they're just doing heavy amounts of steroids. And the reason why the Bulgarians are so good is because, well, the steroid use helped them out, yes. But doing that, they're able to train day in, day out at near 100% of their Olympic lifts and squats. So basically every single day they're coming and training at almost 100%. And that's just, the greater you train, the harder you train, the more intense, with the extra, ideally testosterone floating around, is going to, in theory then, and we seen that, going to lead to massive strength gains. And that's what the Bulgarians were able to do. Now, it's not healthy, but if you're winning gold medals, people don't care about health at that point. You know what I mean? And so what testosterone is able to do is help you to basically recover and keep training at the high intensities all the time. Where normal concentrations, you can only train so heavy, so hard for so long before you start to tire out. Here you see responses in men and women, total testosterone and then free testosterone. They're looking here. 6 sets of squats at 80% of 1 RM with 2 minutes rest between sets. And then the star indicates a significant increase in pre-exercise values. You can see at the bottom you got pre, mid-exercise, immediately post, plus 5, 15, 30, and 70 minutes. So the star indicates significant from pre-value. And then the hashtag #, sorry, I guess hashtag is for social media, whatever. # indicates a significant difference from from women at the corresponding time points. So the interesting thing here is if you look at taken together now, you're not going to see as much response in women. And it's just due to our genetic differences. But for men, it's important if you look at the responses and growth hormone, you see an increased post-exercise as well. We'll get into that here in a sec. But taken together, both of those hormones are there to help out with protein synthesis. So this is why it's important post-workout to get some kind of protein into the diet. Okay, we always joke about meatheads wanting to do they have the anabolic window. You only have a certain amount of time to get the protein in before it's wasted. Well, there's some truth to that. You can see the spike immediately post, and then still elevated 5-15 minutes after exercise compared to pre. Point being is that if you want to build a structure, you need to have the materials there. If you want to build a home, you can't just build a home with no materials. You need actual materials to build something. So if you want to build that home, build it bigger, make sure you get the supplies in, that is, get the protein in, and it'll help out. So the post-workout meal is important to help out with stimulating muscle growth and replenishing. So make sure you get something in post-workout. So training adaptations says increases in response to the demands of exercise protocol and the receptor either increase binding to use, elevated testosterone, they do not due to a lack of need for significant increased muscle-related metabolism. Says other receptors on target tissues, nervous satellite cells, may be more affected at certain time points in training, depending on the window of adaptation available in the target cells. So it's just, once again, it's all kind of going back to training, how you train, and how long you train is going to then start affecting the response of testosterone and the affecting sites that it will work on. It says heavy resistance training using 1 or 2 reps in low volume may not cause any change in testosterone after a workout. Could potentially still increase the absolute number of receptors and thus binding sites available to testosterone. And so kind of that last point says the effect on receptors have not been fully elucidated. What we're getting at this is we know that a heavy stimulus to the cell, heavy stress to the cell is going to start inducing changes right away. Now, to the degree, we're not sure exactly. So you see that last point, or the point before, it says, heavy training with only a few repetitions may not cause a release of testosterone, but you might start changing up then the receptor numbers. And so we really don't know enough about testosterone because, unfortunately, we can't really test it because of, legal issues. It being, a banned substance and illegal, we can't really go and start injecting students up with testosterone and seeing the response. Of course, that would be the best way to start finding out if we could. I'm sure there's a lot of males that would be willing to get free steroids and see what happens. Okay, but there's legal issues with it. That's why we really don't know about testosterone. There's just too many legal issues kind of going through while studying it. But it's definitely an area that should be explored. And not even so much we joke about meatheads wanting to get jacked and look good on the beach kind of deal, or athletes. But what about for older males? Because as we do age as males, as we get older, we start to lose testosterone production. It's just a natural thing that happens. That sucks, but it's what happens. So there is a lot of things we could study with this. It would be interesting to know the real effects of testosterone on the body if we could get to the point to study it. So maybe someday. Okay, getting the growth hormone. Growth hormone has a ton of responses, and we'll see those here in a sec. But it gets released from the anterior pituitary gland. Okay, and you can see some of the responses that it affects right there. But it is important for the normal development of a child. It appears to play a vital role in adapting to the stress of resistance training. And you can see and we'll see in the next slide even more, there's just a lot of responses that growth hormone acts upon. And things that do affect it, you see stress, fitness, diet, age, gender, adiposity, exercise, injury. So any time where you're extra stressed, it's going to affect the amount of release of growth hormone. As we get older, affects the amount of release. Gender, males versus females. Okay, males are going to release more than females. Okay, diet. There's a lot of dietary habits that can change up and affect, too much alcohol intake, for instance. It's going to affect how much growth hormone is being released. Okay, adiposity. Well, that's the more body fat you have, the more or the less growth hormone going to be released. But nonetheless, what growth hormone acts on is, you can see it says decreased glucose utilization, increased protein synthesis, increased amino acid transport across cell membranes, increased protein synthesis, increases collagen synthesis, stimulates cartilage growth, increases lipolysis, enhances immune cell function. So increases renal plasma flow and filtration, promotes compensatory renal hypertrophy. Some of those ones I read off were out of the book, so I didn't have a chance to put all of them on the slide, but growth hormone has impact upon, a lot of different things. A lot. And it does get released to a high amount. And actually you'll see with growth hormone, it being released. So let me play this back. For a large part of these hormones, the more untrained you are, the greater release you'll have. So for like cortisol, catecholamines, insulin, glucagon, the more untrained you are, the worse you have with those hormones. A lot of times the greater they'll be released to stimulate glucose utilization and glycogen breakdown. Partly because those who are untrained can't regulate their blood glucose as well as those who are trained. Those who are trained tend to spare glycogen a lot more and use a lot more lipids for fuel. So if you look at the response of catecholamines, cortisol, glucagon, those who are untrained will have a greater release of those hormones to stimulate glucose breakdown or glucose formation and glycogen breakdown. Growth hormone is interesting because you'll see the greater release from those who are trained versus those who are untrained. And it's interesting because those who are trained, I mean, what he just said, theoretically, those who are untrained have a greater release of hormones than those who are trained. Well, with growth hormone, those who are trained, despite them able to spare glycogen and use a lot more lipids for fuel during exercise, growth hormone still gets released at a greater amount. And that's something no one's real too sure about why that is. There must be some other genetic upregulation that's sending growth hormone out for whatever reason. Now, growth hormone will spike up fairly high following exercise, but not too long after exercise stops does it start to go back down. But still, it's still released after exercise. So that's why it's important post-exercise, just like testosterone. Make sure you get some fuels in. Because you see right here, increased protein synthesis. Okay, get some protein in the diet after exercise because it'll help then start building up that structure. Growth hormones also take in high amounts for those as an anabolic, I'll say anabolic steroid even though it's not considered a steroid. But they'll take this because growth hormone, you can see it says increases lipolysis, but then decreases glucose utilization. So basically it stops glucose going into the cell. So it forces the body to turn to lipids for fuel and spares glycogen basically. So that's why a lot of people take this to try and get really, really super lean. So anyways, those are all the responses of GH. So within females, it says hormone concentrations and hormone responses to exercise vary with menstrual phase. So the mechanisms are very unclear. We're not, once again, too sure with females how it all works, but it makes sense that there's a greater response during a menstrual phase because that's where females are having hormonal changes for that time period. So it makes sense that there might be, a spike in this during the menstrual cycle, but we're not too sure exactly on that. So it appears that GH need to be measured over a longer time, so 2 to 24 hours, to show whether changes occur with resistance training. There's the area in the time curve, which includes an array of pulsatile effects, tells whether changes in release have occurred. And so that's what they're trying to look at is those changes. If you look at I didn't put one in here, but if you look at the way the curve shapes, looking underneath that area right there, underneath that curve. And that's where we're trying to see how that changes with resistance training because we really don't know, once again, exactly all about GH. We know it gets released. We know the basics of it. But it's a hormone that it's hard to measure just because it gets released, but we're not too sure to what extent fully and how that extent then responds. But we know that it does play a major part in a lot of bioenergetics. It's a massive anabolic hormone, and so there's a lot still to be studied with that. It says this is affected by type of resistance training. It says including duration of rest period. It shows that short rest period or short period types of workout result in greater serum concentrations compared to long rest protocols of a similar total work. However, at present it is not clear the various molecular forms or types of GH are affected by rest period durations. Kind of sum this up. We have an idea of GH. We know the basis of it, but we don't know fully all the effects and how it does respond and types of, to a complete picture of its response. Once again, it's kind of like testosterone. A lot of these supplements we just can't give in pill form, like testosterone, growth hormone. You can't just give them as a pill, take this and see what happens. Okay, you need to supply a concentrated amount within the system. That's why with testosterone, growth hormone, a lot of times they're injected. Not a lot of times, they are injected. Okay, that's how they're taken in the bodies, through injection. And so it's something that the IRB legal issues will never be able to get through. So that's why we don't really know, because we can't really test all these the way we should be. Next, you got insulin-like growth factor, and it's just another polypeptide hormone, and it's kind of similar to growth hormone. It's a class of it in a sense, and so has very similar responses as growth hormone as well. And we know it says responses of insulin growth factor: 1, to a multi-set heavy resistance exercise protocol in 3 consecutive days with and without nutritional supplementation of protein, carbohydrate before and during the 1-hour recovery period. And so we know that, kind of like growth hormone, there's going to be an effect when consumed with a meal. And this mass fuel, like it says, a carbohydrate and protein meal. And so that's why it's important to be consuming some kind of meal throughout, just because it will help out then with getting, the responses of these hormones the way they're supposed to be working. So it's important to make sure you're taking a meal along with it, because it will help out over time as well. Okay, when you're adding enough into the system, like I said, nutrition could affect this, just like it affects growth hormone. It does affect, because insulin-like growth factor is basically a derivative of a growth hormone. So making sure through training protocols that you're consuming enough nutrients throughout all the proper time periods throughout the day, and that'll help out then overall with the responses of hormones, the regulation, and everything we've been discussing. Adaptations. This is probably reflected in a variety of mechanisms related to type of IGFs, release, transport, and receptor interaction. It says interaction with other anabolic hormones cannot be ignored, as these often target the same outcomes. Adaptations to heavy resistance training of IGF-1 and the various tissues still require further investigation. So that's kind of a common thread that I keep saying. We still don't know enough about hormones. And a lot of times it's hard to sometimes measure all these, because hormones, a lot of them are targeting the same cells. So it's hard to know exactly, is this hormone really working the way it should when other hormones are targeting similar cells, like growth hormone, testosterone, and IGF. They're all kind of targeting very similar cells. So it's hard to really, you can't really knock one of these out, because you knock one of these hormones out, that could be detrimental to the body then at that point. So when it comes to studying these, it's difficult to really get a full picture, because it's just, there's so much complexity to it all. Okay, then you got cortisol, stress hormone. Cortisol is a group of hormones called the glucocorticoids. That's the classification of hormones they're in, getting released from the adrenal cortex. And it's a major stress hormone of the body. Okay, it gets released in high amounts, especially with higher intensity exercise, or anytime the body's in a stress situation, it gets released in high amounts. Okay, and I say that in a stress situation because it's a very general term right there, but that's really what I'm trying to say is, whether you're stressed from driving in traffic, you're stressed because of work, or you're stressed because you're in a competition, exercise, and training, that's all stress, and that's where cortisol is getting released in all those time periods. Okay, and that's why those who have higher amounts of obesity, higher amount of body fat, tend to have a high cortisol release. Okay, that's why stress plays such a huge impact on the overall health of the body. Because the higher amount of cortisol being released, well, you can see its effects. It stimulates conversion of protein, amino acids into carbohydrates. So it increases proteolysis. It says increasing the level of proteolytic enzymes. Okay, that's what happens with 0.1. It inhibits protein synthesis and suppresses many glucose-dependent processes such as glycogenesis and immune cell function. So really what cortisol does is it blocks the usage of glucose in the cell, and then cortisol does do some lipolysis, but the problem is it is a major proteolytic hormone. That is, it breaks down proteins. So it doesn't really matter if it does help out some lipolysis, breaking down lipids. The fact that it upregulates protein degradation so much, it's the major catabolic hormone at that point. Some circumstances, cortisol release is fine. Like, if you need fuel to keep going in a survival situation, it's okay to have cortisol release at that point. The example I'll always use is if me and a friend of mine are walking through the woods and I hear a bear, a roar of a bear coming out, and I see the bear walking towards us, I don't have to be faster than the bear. I just have to be faster than my friend, right? Because I'll sacrifice him to save myself. Point being, sometimes cortisol is good because you'll sacrifice just in order to save yourself, you'll sacrifice someone. And that's okay sometimes to break down protein, break down amino acids for fuel if it's a survival situation to save yourself. The problem is, in 2020, despite the craziness that's going around us and around the whole entire world and country, take that out, take 2020 out of the picture and just kind of look at modern day Americans. Okay, none of us are in a survival situation. But yet, we have high amounts of cortisol being released all the time because we're always stressed. Okay, you ever been in Houston traffic, Dallas, Fort Worth traffic, any major city traffic? It's horrible. And so you think about in the morning, think of Americans. Well, one, we're constantly stressed all the time about trying to make the bills, trying to make this, trying to do that, trying to keep up with the neighbors kind of deal. We're always stressed, worrying about that. That's a day in, day out stress. And then from there, and some of that is necessary. Sometimes we do have to worry about the bills. But for the most part, a lot of us, we're overstressed. So then we wake up in the morning stressed, and then we're rushing out the door to try and drive an hour and a half to work through traffic. There's a stress. And then we got to, get to a job, and you might have a boss on you, a coworker that drives you nuts the whole day, so you're stressed all throughout the day. Then you got to drive home an hour and a half in the traffic again. And at night, it's hard to calm down. So you think about it, all the time have this high amount of cortisol being released. So therefore, that does lead to greater amounts of adipose tissue. So one of the best things to do when you're stressed, they always say, is go for a walk. This is the only hormone that low intensity exercise will help reduce. That's why sometimes I say just go out and meditate and go sit outside and just be calm, quiet, go pray, something like that. Why does that help you feel better? It's because that calmness will help lower down cortisol levels. But in terms of exercise, going for a walk will help reduce cortisol levels. Now, flip side, that high intensity exercise will have a high release of cortisol. So you gotta be, if you're really super stressed, that's why it's sometimes best not to go do high intensity exercise, because you already got a high amount of this hormone being released. And at that point, then you go and do high intensity, and you have a greater release of cortisol. So you gotta be careful a little bit there. So in terms of I hope you get an understanding of kind of this hormone right here. It does have a greater effect in type 2 fibers than type 1. It says resistance exercise response, so it responds to resistance exercise protocols that create a dramatic stimulus to anaerobic metabolism. Increase in cortisol might not have negative effects in men after a period of training to which the body has adapted. Adaptation disinhibits cortisol levels at the testes, thereby maintaining testosterone's primary influence on its nuclear receptors. Basically, what this is saying is as we train, as we start to adapt, we have less and less release of cortisol. Because the body's not being stressed. Even though you're training, it's the body's got used to that stress a little bit, so therefore it knows how to release. It just releases less cortisol throughout because it knows it can handle the stress basically. And key points: high volume, large muscle groups, short rest periods, increased serum cortisol values. So basically, doing high intensity exercise will have the greatest release of cortisol. It says chronic high concentrations may have adverse catabolic effects. Acute increases still contribute to the remodeling of the muscle tissue and maintenance of blood glucose. Kind of that's what I was kind of saying about just this chronic state of cortisol will have major catabolic effects. Catecholamines, probably one of the most, have the most effects on the body overall, because catecholamines being your epinephrine, norepinephrine, they have an effect on everything. Increased force production via central mechanism, increased metabolic enzyme activity, increased muscle contraction rate, increased blood pressure, increased energy availability. That is, they'll increase lipolysis, they'll stimulate gluconeogenesis, they'll stimulate glycolysis, increased muscle blood flow. So they'll talk about blood redistribution. When we start to exercise, we have a reshape or redirection of flow of blood. Well, that's catecholamines are doing that. Augment secretion rates of other hormones such as testosterone. So specifically, look at epinephrine. It'll increase cardiac output, increase blood sugar and glycogen breakdown, increase fat metabolism. Norepinephrine, properties of epinephrine, but also constricts the blood vessels. Okay, so what happens is as we release one, the other one gets released as well. So they get released in the pairs, epinephrine, norepinephrine generally. So that's why it kind of packs like a double wallop, because one gets released, the other one will get released as well. It says heavy resistance training has been shown to increase the ability of an athlete to secrete greater amounts of epinephrine during actual exercise. And because epinephrine is involved in metabolic control, force production, and the response mechanisms of other hormones, testosterone, GH, IGFs, stimulation of catecholamines is probably one of the first endocrine mechanisms to occur in response to resistance exercise. Okay, catecholamines contribute to everything, pretty much. Okay, and the harder you train, the more intense, the greater they're going to be released. If you don't believe me, go test it yourself. Okay, we said that epinephrine increases cardiac output, so therefore increases heart rate and has an effect on stroke volume. So that being said, go test this. Go run. Let's go do a brisk walk for 1 minute, and go do an all-out intense sprint for a minute. At the end, what's happening? Well, heart rate's up. The 1 minute sprint opposed to walk. Okay, we should all know that by now. But that's how you know catecholamines, the response with intensity. Okay, the harder you work, the greater the intensity, the greater release of catecholamines. The longer you work, the more they're going to be released as well. Reason being is because as you burn up your glycogen, you need to start stimulating glycogen or glucose production. So they'll get released with that as well. They'll get released more in untrained versus trained individuals, mainly because untrained burn up through the glycogen faster, so they need to maintain blood glucose a lot better. Trained individuals can regulate their glucose concentrations. They spare glucose basically in glycogen so they can use their fats more, so they're not going to have as great a response. As we train and get more adapted, the less response to catecholamines, because the body knows how to control itself better. It doesn't need these to be released they don't need to be released in greater numbers because the body is able to maintain all the rates. So the other hormones, insulin. Insulin helps clear out, helps signal the cells to take up glucose. So it's a major anabolic hormone, stimulates protein synthesis, lipid synthesis, unfortunately, and then glycogen synthesis. Okay, insulin's a major anabolic hormone. Sometimes it'll be taken in conjunction with steroids because it'll help out because of the protein synthesis capabilities. Then you got thyroid hormones. You ever get your blood panel taken, your blood panel taken, you'll see T3, T4s. That's your thyroid. Okay, it's thyroxine 3, thyroxine 4 is usually what they're looking at. So thyroids basically, they help out with metabolism, mitochondria, and cell growth, kind of looking at that. So those who have a greater production of thyroids tend to be leaner, or the hormones tend to be leaner. Now, if there's hyperthyroidism, those who have produced too much thyroid tend to be extremely lean with very little muscle mass. And those who have a hypothyroid tend to have higher amounts of body fat. But nonetheless, those who do produce enough thyroid hormones tend to be leaner than those who don't produce enough. You got beta endorphin, and then this has been implicated in growth, repair, pain, and exercise stress mechanisms. It says unfortunately few data are available concerning the responses and adaptations to resist training or exercise. To conclude with this chapter, just remember the key points we talked about. That is, we're talking about hormones which get released from endocrine glands. That's why we're talking about the endocrine system. But hormones are chemical messengers that cause some kind of change within the body. And for the most part, what we discussed was causing the allocation, the production of substrates, primarily glucose. Okay, hormones get released to maintain blood glucose levels for the most part. Okay, another major part is they cause a stimulation of growth, ideally, testosterone growth hormone, causing an increase in muscle mass and increase in strength. Okay, and so just remember the major hormones we talked about: cortisol, GH, testosterone, catecholamines, IGF-1. And just remember the main parts of what they're trying to do. Exercise, for the most part, upregulates them because in a lot of ways, well, there's a stimulus that takes place because you're inducing some kind of training, you're going through some kind of stress, so they're getting released for the most part because you're burning up through your glycogen, through your glucose. So they're getting released to maintain those levels, but also due to the damage of exercise on tissues, things like growth hormone, testosterone being released to help upregulate protein synthesis, to repair and rebuild what was torn down. Okay, so just remember the important parts of hormones, where each one's being released, the major functions, and that exercise, and the greater the intensity of exercise, the greater response of those hormones are going to be. We don't know enough about all of them. A lot of them is hard to test and study, but what we do know is a greater exercise stimulus, the greater release and uptake of those hormones, greater receptors being upregulated as well. Okay, so just remember those main important points, things we talked about, what hormones are, which one's being released, and their overall effect on the body.